A warm welcome to all of you, and thank you so much for having invited me to talk to you about technology developments in our industry, of course, with respect to reduce the carbon footprint of cement production. You all know that cement is such an important material for all of us, for well-being in our world, and the world would certainly look very much different without cement and concrete. And the first slide shows a picture from an air show a television show in our German TV that was on air 1.5 years ago, and you might know it, Who Wants to Be a Millionaire? It's a very famous show. And the question that the young fellow has been given, and I should say that was a €1 million question, so the last. And the question was, what is the most used material globally in weight? Is it steel, cement, plastics, or paper? And of course, all of us would have loved to sit at that chair to give the right answer, because of course the right answer is cement, and we would have loved to take the €1 million. Now, guess what the young fellow did? He didn't accept the question, so he went home with €500,000, not answering the question, but nevertheless, I think he went home very happily. So this clearly underlines, that the importance of our product is really very important for the world, and it's still one of the most used materials. On the other hand, of course, the pride that we have in producing this material and being able to deliver this to the world, the other question, of course, is, how is our product positioned with respect to its CO2 emissions? And this is on our all agendas in these days. In all companies, all associations worldwide deal with the question, how can we reduce our carbon footprint? And the framework, of course, is clear at the Paris Agreement, which really forces human mankind to limit the global warming to less than 2%. And that means for our industry to reach carbon neutrality by 2050. And I'm working in Europe for the European cement industry, in particular in Germany. And we have what is called the emission trading scheme in Europe. And you can already see today, from an economic point of view, that our industry is dealing heavily with carbon reduction. And one of the reasons is also that we have a carbon pricing system. And you can see that over the years, the carbon price, that means the carbon price for a ton of CO2 has developed quite significantly up to the current date. Now, how can we reduce CO2 along the value chain? And you're all familiar with this. There's nothing new for you. I mean, of course, in our hands, we have clinker and cement, so we focus on the clinker production, cement production. But along the value chain, it's a question, how can we use, concrete with the material efficiency higher than today? How can we further use SCM in concrete? And at the end, how can design and construction contribute to increase material efficiency? And this is, of course, also to be seen against the context of less CO2 emissions for construction. And finally, and you all know about this, recarbonation plays a major role. It is, as you all know, now going to be accepted on an IPCC level, and recarbonation will take a place, in the carbon balance on the Earth, on the global carbon balance. Now, I'm concentrating on a few of them, but before I do so, as I'm focusing on the technology aspects of clinker and cement production, I would like to draw your attention to the ECRA technology papers that we have together with ECRA developed, a couple of years ago, and that we have updated a few years ago. And you find all the technologies which are important today in our industry, and that in these technology papers, but also technologies which are upcoming ones, and which, of course, can develop in the time to come. It's really worth reading these documents. Now, let us first concentrate on the aspect of cement and concrete before I then go back to clinker production. And these are the points I would like to concentrate in my presentation today on. Now, cement and concrete. The question is, how can we, produce in the time to come cement with optimized clinker content? How can we produce concrete with optimized clinker content? So it's the same question, but put differently. And the question finally then is, how can concrete be used efficiently in construction? And now I'm not going to touch upon all of these aspects here, but I will only underline a few of them. But the most important thing I would like to highlight is this, is I think it's a unique process that we are going through in the time to come, and it really requires the good cooperation along the value chain. It's not fully in our hands. So we need our downstream users to participate, and we also need framework from governments, for example, from policymakers, but also from the society to deal with this, to make this happen, and finally also to buy the respective cements and the respective concretes. Now let me draw your attention to cement first, and I would like to give you an example here of our European situation, in which we have a cement standard which is called EN 197 Part 1. And what you can see in this triangle here is one example, for what we call the ternary cement. So it consists of clinker, slag, and limestone, and each corner is representing clinker, slag, and limestone respectively with the corresponding letters. And you see on the left side, you see the slag cements in orange, and these are well known, and you know that slag cements are well established in our industry. And on the bottom, you see the limestone containing cements, the one in blue. And you all know also that limestone content in cement is limited for very good reasons, differently from slag, for example. Now, what is new in our 197 Part 1 since a couple of years is that we have ternary cements which contain both slag and limestone. And it's not the only composition here, only combination that is possible. Other combinations are possible as well. But I'm concentrating on this one here as an example. Now we have the possibility to enlarge this standard, and it has recently been published. So we have now new cements in our European cement standard, and these have higher concentration, as you can see here, of limestone. So that is very good, and we have been able to prove that not only the constituents are well tried and proven, but also that the concretes are robust and stable. Nevertheless, it still requires, of course, the national concrete standards to be adapted, and you should know that the concrete standards in Europe are not harmonized ones all over Europe, but they are standardized on a national level. So these cements are available right now already, and these are clinker-efficient cements which we did not produce in the past, and which, of course, were not able to be used in concrete, but they are available in the near future. Some companies are already producing them. And of course, we have to make sure that concrete standards allow for its utilization. So I will not bore you with too many details and tables here from that standard, but what you can see here in the upper part, the main constituents. Beside clinker, you have all the main constituents that you all know, from blast furnace slag down to limestone. And so far, it were, all these main constituents were in the standard, but not for each of these cement types. And what you can see here, the one in red, these were the ones which were still lacking, focus. In particular, when we're talking about ternary cements. And that has been all broken down, to cements, which you can see here as so-called CEM2 cements, for example, which now have a composition of three main constituents, namely clinker, and a mixture of the other main constituents as they are laid down in the standard. So it's a great opportunity for our industry to build on this and to make sure that these combinations as ternary cements can be used in the future. Is there a further development beyond this, beyond these cements which are standardized at this point already? And the answer is yes. We have a strong focus here at VDZ at limestone containing cements. And when I talk about limestone containing cements, I'm talking about limestone contents of up to 50%. And we all know that limestone, of course, is only to a small degree reactive in our cement. So different from puzzolans or, for example, from slags, as we all know. So we have been focusing on this, and it clearly shows that these cements have a high potential. It's not only the limestone content, but it can also be combined with other two materials, like slag, for example, in this example, or with clinker. And of course, the possibility for the cement producers to produce these cements is there. Again, it needs the adaptation of the respective concrete standards. And this requires some careful thinking, because these cements cannot be used under all conditions. And we know from our traditions that, of course, most concretes are made in order to fit for any purpose. And this is, I think, something that has to be changed and to be adapted in the time to come. As we all know, there are concretes for dedicated applications which require good strength development and maybe protection against carbonation, but that's it. So in countries like ours, where we have frost, for example, and de-icing salts, so these are dedicated applications where, of course, such of these cements should not be applied. But for most of other applications, these cements can be applied. And this is what we are building on. And I think, with this customized approach of these cements in concrete, we will have great opportunities to bring these low CO2 or low clinker or clinker efficient cements to the market. Now let's have a look at the clinker, which is of course the heart of our value chain, with our kilns, for example, but also with the big investments, and also with the question, how can we reduce CO2 from clinker production, for example. And you all know that we have a couple of possibilities here. And one of the pathways is to utilize alternative fuels, and of course also alternative fuels with biomass. So what you can see here is an example of our own industry here in my country, the German cement industry, and it shows the substitution rate of alternative fuels. And what you can see is that we are almost up to 70% substitution rate, and that is the average of our country, saying that a couple of our kilns are basically operating close to 100% substitution rate on an annual average base. So how did that happen? It started already in the 90s of the last century, and it started with used tires, of course, but also with PCB contaminated oils in 1990. The government asked the cement industry at that time, what could be done with the PCB containing oils, and they asked, whether the industry would not be willing to incinerate these PCB containing oils. And of course, the industry was hesitating at that time, but that they made it, and that was a big breakthrough, because of course it was a full proof, of the destruction of these persistent organics. And that was very good, because it was together with the government that has been developed in the 90s. Later on, of course, other wastes were also used, like industrial waste from defined origins, which of course need to be pre-treated. And what was helpful in these days was the waste landfill ban. Sorry, that means starting in 2005, it was clear that waste that still contain organics up to a certain degree were not allowed to be landfilled anymore. And a whole waste management industry developed in order to make sure that existing wastes are pre-treated, sorted, and that some of these materials, of course, found their way, for example, into the cement industry. There were other waste streams coming up, like animal meal, at a certain time when there was a big need, to get rid of these materials. But also the question of sewage sludge was a burning issue for many municipalities. It was still used as fertilizers, this material, but it was clear that our today's municipal sewage sludges are probably not the best to be used as fertilizers for agriculture. And that was the start, of this material to be used in the industry. It's mostly dried sewage sludge, of course, and it's well treated within a couple of cement plants here in our country. Okay, as I said, the substitution rate already up to almost 70%, which is, I think, looking back, a big success of the industry, and also, of course, the work that we did here at VDZ together with our companies. Now, utilizing alternative fuels and making sure that these fuels have sufficient biomass, for example, is partly reducing our CO2 emissions, of course, for good reasons. But it's only affecting the part from the fuels. And as you all know, we have the CO2 emissions from the calcination of our limestones, which is, as you all know, 2/3 of our total emissions. Now, we have been working here at VDZ together with ECRA, the European Cement Research Academy, for many years on the question, how can potentially CO2 be captured at a cement kiln? And we have been focusing on two technologies, basically. The one is called post-combustion, and the other one is called oxy-fuel technology. You may know that post-combustion is a tail-end separation. That means you basically have a scrubber at the end of your kiln. It's kind of energy intensive as compared to other technologies, but it's well tried and proven in other sectors. And an important project here in Europe is going on at the Norcem Brevik plant of Heidelberg Cement. Other prototype testings are on their way. Oxy-fuel technology is slightly different. So what you try is, you operate the kiln without combustion air, but instead of this, you use pure oxygen. And in theory, if the kiln is nicely sealed, you have a high percentage of CO2 in the flue gas, which is much easier, of course, than to be processed. And processed means you clean it, you dewater it, dry it, but at the end you compress it, and you have then CO2 in a liquid state. A couple of projects are going on. So we have an ECRA project here, which we have been working on for a couple of years to develop this kiln. Other companies have pilot tests underway, and I think it's very promising what we feel here, because also the equipment suppliers have taken this as an opportunity to further develop this technology. On the right hand side, you see a graph in which you can get a feeling of the cost, and these costs are not entailing yet containing yet the costs for further processing of the CO2 or for storing, because these are the big questions, of course, what to do with the CO2 at the end, beyond, of course, the high capex and operational costs that go along with this technology. There are a couple of projects to be mentioned here. When we talk about oxygen, the oxy-fuel, the first generation oxy-fuel project has been developed. The first kiln is now as a pilot kiln to be set up in the southern part of our country. It is, by the way, already the second generation of oxy-fuel technology. Now you may wonder, why it's a second generation. There are some subtle differences or details, which equipment suppliers were able to overcome. And it's now available that these kilns are much smaller in size for the same capacity, much less equipment with other challenges, of course. But it's a very nice development of what has been developed here a couple of years ago, in particular by the European Cement Research Academy. Now, post-combustion projects, as I said, a couple of them are available and have been announced. The most famous one is the one of the Norcem Brevik project. It started already some time ago, and the idea is, to capture the CO2 and to transport it to depleted oil fields in the North Sea, which of course is very convenient to have, a plant next at the coastline, in which it's very easily possible to transport the CO2 by boat or by pipeline into these depleted oil wells. Another project is going on in northern Italy. It's integrated calcium looping. It's slightly different. So what you do inherently, you lose the calcium oxide that develops in a kiln, to make it as an absorber for CO2. And once you recycle it, you are able at the end to have a CO2 stream which is quite pure in CO2. That means very high CO2 concentrations, which of course makes the capturing, or let's say the further processing, of course, highly efficient. Another project is dedicating on the utilization of CO2, which is the second big thing, besides the potential storage of CO2, namely utilizing the CO2 for something, for example, in the chemical industry, or for example, as synthetic fuel for the airline industry. It's a project that has been announced, which is in cooperation with wind energy providers, which take advantage of excess wind energy when the wind is blowing and the electricity demand is not as high as to utilize all of this energy. Part of the team is also a refinery in which this CO2 and the hydrogen is then made to react to, for example, methanol or kerosene as, for example, synthetic fuel or other base chemicals for the chemical industry. That clearly shows, and when we are able to combine, this with other sectors which have a need for our CO2, for example, or which can provide renewable energy at good costs, then there is an opportunity, of course, to utilize the CO2, which is, of course, a great option for our industry besides storage. Now, coming back one slide here, with respect to storage, and I think the situation will be similar in many parts of the world. But I'm concentrating here on Europe, of course, because that is the area I know the best. There's quite a bit of testing going on and exploration going on, and also studies going on to understand where CO2 can be stored, for example. But this requires, of course, first of all, to know exactly the sources, but also the question, what kind of infrastructure do we need? And the European Commission has a strong focus on this, and many cement producers are participating to make sure, that a good infrastructure for CO2 and also for hydrogen can develop, which of course is necessary for our industry to utilize carbon capture technologies. And it doesn't make a difference whether it's for storage or for utilization. So we kind of need an infrastructure, and of course this is nothing which the cement industry can do. We need this guidance or this framework to be provided by our countries, of course. Now, a short word on the mitigation potential through CO2 utilization. The right-hand side shows, in a very complicated and busy diagram, the many options that CO2 can be used for. And of course, when it's captured CO2, that CO2 has a benefit for the downstream industries here. And it's basically the chemical industry, and you can talk about methanol, you can talk about polycarbonates, you can talk about e-fuels, for example, you name it. So there are many possibilities. And one of the reasons is that not only there is a need, to make use of our CO2, no, even further, the chemical industry has, of course, a long-term interest into, basing their value chains on carbon. So far, it's all based on fossil carbon from the petrochemical processes, of course. And there's quite a few numbers are available, but the ones, I would like to highlight here is one for all over Europe. The chemical industry in Europe has put together a report, and they have stated that for low carbon energy and feedstock for the all European chemical industry, they would require almost 400 million tons of CO2 every year. That is 4 to 5 times the amount of CO2 that is today emitted by the cement industry. So I'm saying this, that there, to underline that there is a potential for our CO2 to be used. There are, of course, challenges and obstacles, but I'm sure that we can somehow overcome this with the respecting guidance by the governments, with sufficient and viable, economically viable renewable energy, for example, and so on, and also in combination and cooperation with others, like, for example, the chemical industry. So I think in the long term, this is a very good solution, and honestly, in the medium term, for some projects, it might be really useful also to look at storage, because storage is the only possibility today, to get rid of CO2 or to eliminate CO2 from the atmosphere at a larger scale, at to say so, comparable, viable costs. Now, concluding this all, I think that we can, as an industry, we can effectively reduce the carbon footprint. Yeah, but it requires that we include the whole value chain. I've been talking today about clinker and cement part, which is in our hands, but we have other parts, of course, where we have to cooperate with, downstream users like the ready-mix industry, the precast industry. We have to make sure that CO2, embedded CO2, finds its place in construction. So far, this is not. There's no pull effect from the market when it comes to CO2 efficient cements. We have the difficulty in our country that, of course, we are able to produce these new types of cement, with low clinker factors. But the question is, are they going to be bought, by our customers? And therefore, we need this kind of push and pull, or to say it in my words, we need a strong and trustful cooperation along the whole value chain. It's not fully in our hands, but I think that we have been able to express the need here to cooperate along the value chain, because this is something that we have to do in common. We have to really get to net zero CO2 emissions by 2050 for cement and for the concrete sector, and that means, that we cannot do it without the cooperation with others. Now, I've been talking about clinker. To summarize this, and the thermal efficiency is one thing. You're working on this for many years. I've been talking about alternative fuels, which of course is state of the art, but it requires, of course, the respective waste management, in the neighborhood and the area of the cement plants. I've been talking about cement, and that we still have the potential to reduce clinker content further through substitution by SCMs, in particular limestone slag, but also, and I've not been talking about this in detail, by calcined clay, which is something we are looking at in great detail all over the world, because it's a promising main constituent in cement that can also contribute to cement performance respectively. There are opportunities, of course, for new binders, but so far I think the main focus is still on Portland cement clinker. And the reason is the sheer amount that we need of clinker and the possibility to source the raw materials locally as limestone and clay. And this is most important, and it's a big prerequisite, for our value chain to make sure that we have sufficient raw materials for the amount of cement that we still need in the time to come. And finally, I've talked about carbon capture, and I think, it's an upcoming technology. It's not easy at all, but in principle, I believe, that this technology can, or must play an important role in our industry, and it will play an important role in our industry. Technology-wise, I think we have understood quite a bit of this technology, and all the parts of this technology are mature enough to be implemented in our sector. The big challenge is what to do with the CO2 at the end. There is a possibility of storage, as I said, but it's also the possibility of utilization. And I think time will tell, that utilization, of course, in the long term will play a much bigger role than today. And these days, I think there will be certainly, works to be started with the storage of CO2, in particular at cement plants which have access to the respective infrastructure. So I'm at the end of my presentation. I thank you very much for listening. I really would have loved to be there in person. And, it's really sad, that I can only talk to you through this video. I hope that we might have the opportunity to see each other in person sometime in the future. Thank you so much.